What's up, guys? Welcome back to Hallway Channel. We're gonna finish 2.4 today. Skippy toilet.
Ohio. All right. So as we go through this, we started this problem, and I probably started it. Don't understand that lingo, but obviously I've heard it. Looking at stuff. There are really two options to physics, and when you're doing physics problems, you're going to take one of two routes through a problem like this. Now, I want to stress, nothing that we do mathematically goes beyond anything that you'll do in Algebra 1. It might feel different because we're changing the letters and stuff. We'll deal with that, I hope. But there's two options. And instead of making it ugly the way that I was starting to the other day, I'm going to show you first how I do it, and then you'd let me know if you like it or hate it. I won't be offended either way. I'll probably use both of them. But I want to make sure we can see everything that's happening here. Now, going through this. We have a ball that's falling, it's accelerating, it's going faster, and it hits the ground going so fast, and we want to figure out how much time did it take. As we look at this, the option that I would naturally go with in doing so is option 1, and I'll just do it over here because we'll have another one in a minute. Option 1 says the following. Solve, and I'm going to use some math language here. Solve the literal equation. And remember, EQN is my shorthand for equation. And what are we solving it for this time? We're given all this and we're finding time. So I'm going to say for delta t, then plug in values. This is when I do physics and stuff, and I'll use values. This is how I would prefer to do it. And the only reason that I would prefer to do it this way is because right now we don't have any ugly numbers. But is it possible that my velocity was like negative 49.0325 or something, like some ridiculous decimal that I don't want to have to write over and over and over and over because it's an ugly number? When I look at these problems, I want to solve it and then plug in. So I'm going to take all my vector markings off. I'm not going to use the arrows because it's going to make it look easier. Cool. So here we are. A is equal to, and I'm just going to rewrite that equation, VF minus VI, and then are we agreed that if we start timing, we start at 0? Yeah. So instead of delta t, if I just write t to make it a little bit simpler looking, can we handle that? No vectors, no delta, we just have this. I want to solve that without ever plugging anything in for t. Now, right now t is where in my problem? How would you describe it? The denominator. That means I'm dividing by t, right? If only we knew what the opposite of divide by t was. I'm going to multiply both sides by t. Now, I don't know how Russell is your algebra teacher, right? I don't know how Russell writes it. And I want to try to stay consistent. Does it feel more natural if I do this and say times t? Or does it feel more natural if I actually just write the big parentheses here and do it?
I'd say just no parentheses, just times t, no arrow.
Yeah, no.
What? So just like this, times t?
Yeah, that's it.
And times t.
Yeah.
Okay. Now, on the... It can be. And yep, there might be subtle differences here. Why did I multiply by t again? Not to get rid of it, not entirely. To get out of the denominator. Now I'll accept the word cancel. I hate it, but I'll accept it. Are you guys okay? I'm going to rearrange. I'm going to call this AT instead of TA. Everybody okay with the math that says I can rearrange that? Okay. I'm trying to solve it for what again?
Seconds or time.
So time. And which variable is time in that equation I just wrote? T. Unfortunately, right now, my time t is being multiplied by what? All right. Heading. To make this say only t, how do I move this acceleration?
Divided by.
Good. I'm going to divide the left side and the right side of the equal sign by what? A. So we'll do it here. And I'll try to stick and change colors. Divide by A and divide by A. What happens to the A on the left side? They gone. Cool. Now, this, I'm going to rewrite it all in one color. Have we solved it literally for t right now? So when you say basically, tell me how I haven't.
You have to plug in the numbers up.
Good. So I haven't gotten a value out of it yet. I agree 100%. But I have solved it in terms of, I have t equals. Now, the other reason that I do this is because units can be messy. And they're going to be messy for a second. This part is by far the hardest math that we do. Remind me what happens when we divide by a fraction.
Decimal.
You could.
Oh, no, what? Divide by a fraction?
Sorry.
Reciprocal. You multiply, do the wall.
You do the whoa, you multiply by the reciprocal, right? So last little thing, help me out. I'm going to do my unit game over here on the side so I don't have to carry it through. The velocity that I was given, what's a unit on velocity? So check this out. I'm going to write it like a real fraction. Meters per second divided by, what is the denominator's unit or the unit on acceleration? So can I just say meters per second squared? Okay. It's ugly for a minute, but this is our check to make sure that we get the right thing. When I work through this calculation, Rodelia, what should I have left as my only unit if I'm solving for time?
You should have.
Don't do the math. Just tell me, when we talk about time, it's measured in what? How do we measure time? There's a bunch of it. What were you going to say?
I don't really know. Seconds.
Seconds. We should be left with seconds, right? That's my check. Now, I'm going to do this little scratch work over here. This becomes meters per second times, what's the reciprocal that I'm multiplying by? Okay, they gone. And here's the hardest part. What happens with these? Okay, if I do this, understand that or no? So some of you might. If you don't, check it out. I'm going to make one little change. What? Not that big of a change. If instead of writing seconds squared like this, what does it mean to square something? You read that just seconds times seconds? Now that one's gone and that one's gone. And that's gone and that's gone. What's the only thing that's left? A single unit of seconds. Is that how I should measure time? I'm feeling good. I know that my work is done in the correct way. Now we just need to plug in. Using the values that we have, what is the final velocity? So negative 49 meters per second, which I already know it's going to wind up in seconds. I've done all this, so I don't have to include it. Minus, what's my initial velocity? 0. Divided by, you might have 9, almost. Negative 9.8 minus, and this is a weird one. What was my initial acceleration right before I dropped it? 0. Okay, we don't really need those, right? I'm just showing them that they're there. On your calculator, you think you can do negative 49 divided by negative 9.8?
5.
Not quite. Is it exactly 5? It's exactly 5. No, it is. It is. Now, if it's a negative divided by a negative, there's always issues on typing into your calculator. Can we just ignore it?
Yeah.
Okay, this is going to wind up to be t is equal to 5.0.
Seconds?
Seconds. Thank you. Now, this is the way that's more natural for me to do the problem. I like to solve it and rearrange it without ever plugging numbers in because I get lost in the numbers if they're ugly. Does that feel unnatural for some of you? Probably, realistically. But let's check something else real quick. If you like this, cool. I would suggest use that. That's the way that I do it. Alternatively, though, option 2. And we better get the same answer. If we don't, something's wrong. But I want to make sure that you guys have one of at least however many choices we can come up with to work your way through a problem. Option 2, instead of solve and then plug in, what would the order be? Could you plug in first? Then solve? So let's just see what happens in that one. If I plug in first, what's acceleration? What am I plugging in for that? Careful. There it is. Negative 9.8 was the acceleration given in the problem. And we'll see where I don't like this. What's my final velocity? Negative 49 minus 0 over, can I just call it t again? Okay. For this one, can we solve for t? Gian, how do you undo a divide by t? How do you undo divide by t? How do you undo? What's the opposite of dividing by t? And like, before just giving the answer, which that's okay, I'm glad you know it. It is multiply. Yep, absolutely. So we'll do the same thing. Times t, and Dagon. How would you guys, with your algebra abilities right now, rewrite this? Negative 9.8t. Okay. Is equal to negative 49. And then to solve for, to solve for t, what's the last step, Ash? So we'll divide by negative 9.8. That is really bright, so I'm sorry if that's hard to see. Dagon. What's the only thing that remains on the left side? And that's what I'm after. And it turns out it's negative 49 divided by negative 9.8. The issue that I have is a unit game is harder to play here. Now, if we don't want to include units throughout the entire calculation, which I don't really, just so you know, we have to be able to follow through what we plugged in. So I'm already thinking this was meters per second squared, and I'm writing it above. I can write it below. And this is the unit game that we have to play to make sure we get the right thing in the end. This was meters per second squared, and that was meters per second. And then when I divided by that, it's like taking my meters per second over here and multiplying it by what? Not t. When you divide by meters per second squared, it's s squared over m. And we can play the same unit game, but it's harder to keep track of stuff here. Of these, I don't have a strong preference. I'm lying. I do have a really strong preference, but I'm cool to go either way with this. These two options, they're the same problem. Real quick, if option 1 of solving it first and then plugging in feels more natural, throw up one hand. If option 2 of plugging everything in and then solving it feels more natural, throw up both. And I'm just curious to see, like, everybody vote, don't abstain. Option 1 is plug it in and then, or solve it and then plug in. Option 2, two hands, you like to plug it in first. All right, so I feel like we're at a protest. That's okay. We're gonna go with the second one. The unit game is gonna be rough. We'll get through. All right, last thing. Anytime that we write a problem with context, what's the actual answer to this question?
How long did it take?
So how do you put that in the context of the problem?
It took 5 seconds
For what to happen?
for it to reach the ground.
Boom. 5.0 seconds
To touch
for the ball to fall.
to fall.
Okay. These problems, with the exception of the units, hopefully there's nothing mathematically about it that's like intimidating or scary. It looks a little different than algebra, but these are just multi-step equations, which is what you were doing last week in algebra. Okay, do we need to do another one like this, or can we move on? All right. So we are nearly done with the section, like really fast stuff. Everything that we've done thus far has been in one dimension. Now, all that means is up and down. That's a straight up, like vertical line. That's one dimension. The x-axis is a single dimension. How many things take place in one dimension in our world?
Up, down, side, side. Right?
So, but if you have up, down, and side to side, how many dimensions do you have now? You have a vertical and a horizontal. You have 2. So, I'll tell you, not many things take place in one dimension. We better real quickly hit on two-dimensional motion. Two-dimensional motion.
Where is it? Is this chapter 2.4?
Yep, we're still continuing on. We have a couple little things to talk about here. So the last main topic was probably velocity and acceleration.
2.3.
Are you sure it's 2.3?
Yes.
It is 2.3. Yes, you are correct. I'm sorry. Okay, two-dimensional motion. Now, as we look at this, a couple things that we have to go through. Give me an example of something that should be modeled in 2 dimensions. This dropping, if I hold it here and I drop it, that was just single dimension, right? Now, more commonly, though, stuff isn't just dropped and we deal with it like that. How else could I have this hit the ground without just dropping it straight down?
Move it down yourself.
I could just do it myself, right? Or if I do this, did it still hit the ground?
Yeah.
How many dimensions did it just travel through?
2.
So you might think 3, I would agree, but let's check this out. Realistically, in our world, we're going to think 2. Because as it fell, it moved down, but it also moved how?
Right.
To the right. So there were 2 dimensions there that we had to deal with. As we get through here, there's a big statement that I want to make sure that we have. We're going to say that just changing directions, which, if I change directions, do I have to change my velocity?
No.
So I'm going to make a claim, and I want you guys to tell me agree or disagree, and I want you to come up with an argument. My claim right now, I'm going to give you about 30 seconds to chat with your neighbors. If I change directions, I must change my velocity. I'll even write it here. I want you guys to talk about it. Change direction means change in velocity. The question is just whether that's true or false, and I want you to justify it. Means change in velocity. Talk it out with your neighbors. I'll give you about, I don't know, a minute. If it's true, explain it. If it's false, explain it. I heard several groups talking about one really good thing. A lot of people said no initially. I don't have to change because of the following. I'm walking at a speed of 1 meter per second. I'm turning and I'm still walking at a speed of 1 meter per second. Did my speed change?
No.
No, but that's not the question at hand. Speed and velocity are different things, right?
Yes.
They're super close to each other, but what's the difference?
One direction.
If I want to change direction, do I need to change direction?
What?
Like, I'm not trying to trick you. It's a weird question. To change direction, must I change direction?
Yes.
Boom. And to change my direction means I'm changing that velocity. Boom. It definitely means that if we change direction, we must change our velocity. So we're going to tie that in and say the following. Changing directions must occur with a change in velocity. Now, man, there's another way that we could word this. If I want to change my velocity, like the difference between this velocity and that velocity, there's another word for that. We talked about it at the start of class. It was one of the things that we wrote. Acceleration. To change direction, we must accelerate. To change direction, we accelerate. Now, that's a weird idea, but we're going to be able to think this out. The easiest way to envision this and to think about it is we're going to think about circular motion. Almost like a merry-go-round if we need to. So, we'll have that here, and we'll stick with this color. Circular motion. All right. So, couple things. I wish I had a cup that you could see. There's liquid in this. It's soda. If I do this, does the water, like the liquid in here sloshes a little bit?
Yes.
Okay, as I go this direction, what side builds up liquid?
This side.
It's like this, right? It gets gathered over here. And if I go really fast that way, all the liquid in here gathers up like this. Like it bulks over here. Everybody seen that happen before?
Yes.
What direction am I accelerating right now? I moved to your right, and what direction did the liquid in here seem to be pushed to?
Left.
It went the opposite direction, right? So as we think about this, I want us to envision just a nice merry-go-round. We don't have to draw it real fancy. But let's consider the following. I have this going on. If I'm on a merry-go-round and it's spinning this direction, yep, I would draw this. I'm going to try to make it a circle if I can. I won't be able to. That was actually pretty close. Okay. If I'm on a merry-go-round and I'm riding on the outside, centripetal force, which we haven't spoken about that yet, but you've probably heard it. If we're going real fast on this merry-go-round and you let go, what happens to you?
I don't know where you
So you might fly. So let's say hypothetically, you're hanging on right here and this thing's going super duper fast. And I let go. I'm going to be spit out. Realistically, it's probably going to go like this way. But if I hold on, it's pulling me outside, right? If we're going fast enough, I could hang on with just my arms and I would, it'd be pushing me outside. Let's use that soda example from before. If I am being pushed to the outside, it means acceleration is in which direction?
The opposite way.
The opposite side that I'm getting pushed. So if we look at this and we say, hey, look at all these velocities going around this thing in a circular fashion. Acceleration to turn this must be going which way?
The same way as the velocity.
So careful. You don't have to draw this. Here's our person hanging on. They're a weird person, but that's okay. So there they are. They're hanging on like that. They're being pushed outside of the circle, which means acceleration is pushing which direction? Opposite of them. So straight to the inside of the circle, right? As we look at this, I'm going to change color for mine. Acceleration is typically represented as violet in your textbook, I believe. All of a sudden, we see that we, to change direction, must accelerate inward. Now, it's counterintuitive because we're being pushed outside by acceleration toward the inside. We've all felt this, I imagine, on merry-go-round. Although I don't know, is there a merry-go-round here?
No.
There's the stand-up one that's at Pirate Park now that you can stand up and spin on. That will do the same thing with it. Okay, all of these are my acceleration. As we think about this, this is a nice and easy example that we can all envision. we have a special type of acceleration. I said the word a second ago. Do you remember what it's called? So that's the color. Centripetal. Acceleration. Now, on a curved path rather than a circular one, it might be more natural, but we'll think about this. Centripetal acceleration. Big, fancy, ugly word. I'll give you guys a second. I'm just trying to get an eye on when people are writing. Okay, by definition, super easy. We're just going to say this occurs and it happens toward the center of a circular path. And it happens with everything. And we see its impact on everything. Anytime you go around a corner, if you've ever just imagined what that liquid's going to do, you can pick it out. If and you don't have to draw this, I'll use this red color to say don't draw it. If I'm I'm going down and I turn this direction. If I have a cup, what way is the water going to try to go? It's going to go out this direction, isn't it? Which means my centripetal acceleration would be where? It'd be pushing that way. And it'd be pushing that way less over here and less over here because as we go, it's going to start to pull me less. But you can feel this every time that we're moving around. Okay, that idea, okay, first off. Okay, I don't want to talk a ton about it if we don't have to. Centripetal acceleration happens anytime you have circular motion. The last little piece, and it's the very final thing that we're going to write for the entire chapter together, is we need to think about projectile motion. And if you guys never played with them with Miss Forfietta, we do have projectile launchers. We will be launching stuff at some point. Yes. We're going to do an egg drop in here as well. Sometime during chapter 3. All right, so this is the end of chapter 2. Okay, so it's going to look ugly in my notes, but I want to be able to see it. The last little piece that we're going to talk about, hate it, is projectile motion. So I would do it underneath, and I can start it here, I suppose, but I'm going to run out of space. Projectile motion is our focus here. Now, when you hear the word projectile, what does it make you think of? A gun, probably. That's what I think of.
Actually, no, like a launcher.
Ooh, also gross, but it works just as well for our example. Maybe that's the one that we'll use. Okay, maybe you think of vomit. Blah, like, it's going to do the same thing. Okay, as we look at this, when something's launched or shot from, like, a launcher or a person, if they're, like, projectile vomiting, gross, we're not going to stick with that one. Motion really happens in 2 dimensions. When I threw that marker earlier, I threw it that way, right? Yeah. Now, as it started falling, was it still moving that direction?
Yes.
How else was it moving, though?
Down.
It was moving both of those at the same time. So we're going to refer to those as components. Objects, and specifically they're projectiles, but I don't want to write the word. Objects travel in 2 directions. And then I'm going to sneak this word in parentheses. I lied. 2 directions, comma, or, and you're going to hear me refer to this all the time, components. And I'm going to write it in all caps, but it's not really its own vocab because it's just kind of snuck in there. When we talk about the components of motion, we're just talking about the directions that go in to make the final motion. So, here's what I want us to think about. And it's a quick and easy picture here. Let's say we have somebody standing on a cliff. And here they are. Now they're going to throw something. And it doesn't have any thrust, so there's no boosters or anything like that. But they're going to throw something. And they're going to throw it straight out. If they throw this object straight out, do you agree its path is going to look something like this?
What if it's heavy?
So we're going to assume that the object was the right weight for them to throw it like this. Or it'd do something like this. If you'd rather, yeah. I'm going to make it more obnoxious so just so I can think about it. Okay. As you do this, at every point of this trip, whatever they just threw off the cliff is traveling in 2 different directions simultaneously. At this point, if we think about the velocities of this object, it's going to the right, and I'm going to use like real size here. Let's say it's going that fast to the right. How fast should it be going down, do you think? Faster? Like right after I let go of it, is it being pulled down really fast, or is it going more horizontal than it is down? More horizontal, and I can see that here. So maybe it looks like this, just a little tiny down arrow there, or a little tiny down vector. Now, we work in the nicest possible physical world, which means we don't have to deal with air resistance. If there's nothing to slow down a ball that I throw, is it ever going to change its velocity that way? No. So if we go to, I don't know, this point, hypothetically, its velocity in the horizontal component, or the x direction, however you want to word it, should be the exact same. What happens, though, with its downward speed? Is it going down faster than it was before?
Oh, yeah.
So if I asked the slope of this line and compared it to the slope of this line, way steeper, right? I think it is going down faster. And I don't know how fast. I'm just going to say it right there, maybe. And I'm going to move that up because that's going to drive me crazy. We'll do it here. Still the same amount that way, but now it's going faster down. How about down here? Is it still moving to the right?
Yep.
Did it slow down?
Yes.
You think it slowed down?
No, there is not really right. Yes.
Why would it slow down?
Because it's starting to just go down instead of moving to the right.
So that's okay. It turns out, and maybe this is just against our intuition, and that's awesome that it is. If there's nothing to stop it, like air resistance, it's never going to slow down. You guys ever watch the show Futurama?
Yes.
Yeah.
I love Futurama.
Have you watched a bunch of them?
Yeah.
The episode where Bender becomes God at some point. Like, it's a weird episode of this different colony. Anyway, he gets launched off of a ship. He gets shot out, and he never stops. Now, he does some stuff to make himself stop, but if there's nothing to slow us down, we're going to keep going just as fast. That's not what happens in our normal world because we have air. But as we start going further and further, I go faster in the downward direction. No faster, no slower horizontally. These components in projectile motion, just this basic idea is what's going to allow us to start like having a car moving across and launching a ball into a moving car and see if we can do it. We have the mathematical ability to do it, and it all stems from this. Does it go faster in the downward direction?
Yes.
Why? What would cause it to go faster or to accelerate downward?
Gravity.
Oh my gravity. Cool. That's it. That's everything I have for you. Cool. So, for the next, hopefully, 15 minutes, I want you to work through a few questions, and then we should probably start talking about the test. Cool. I'll let you do this first. Right meow. Not that. We'll go super cool song. We'll listen to it in a minute.
Music bounce
That distracted me. 9, 16, 24. Okay, I'll just go here first. You guys get the privilege of working right now for the next 15 minutes on homework. We're really only in 2.3? Why did I call it 2.4 this whole time?
Because like you didn't like chapter 1 or something. You like
Yeah, there's something weird. This is going to look weird in your stuff, but I'll fix it. 2.3.2, I guess. So all this means when we see... Wait a second. I'm all confused.
That's his last thing at 2.4.
I'm super confused. Yes. You guys got some stuff back at the start of class, right?
Yeah.
Check it for me real quick.